I want to welcome everyone today to the first of our, official Bowie seminar meetings. These will be monthly, going on for the foreseeable future, and we're lucky enough to have one of the newest members of, the Academy in the UK joining us with Ryan Macdonald of the University of St. Andrews. Many of you probably know Ryan. He has been on a lot of these sort of the seminal modeling papers and analysis papers from JWST. And today he's going to talk to us about atmospheres on rocky exoplanets and some of the early results that we've seen in JWST. So Ryan, the floor is yours.
Great, thank you very much for the introduction, Duncan, and to the organisers of the Vogue Plus seminar series. And it's so good to be back in the UK. As many know, I did my PhD in the UK, and I've just come back after 6 years of postdocing over in the US. And I'm really excited to be part of this wonderful community in the UK again, and strengthening the exoplanet atmosphere community in Scotland in particular. So, atmospheres on rocky exoplanets, and in particular, rocky exoplanets orbiting M-stars that will be the focus of this seminar today, are one of the big cutting edge questions that we have in exoplanetary science. So when rocky exoplanets around M-dwarf stars were first discovered, I'm sure all of you will have seen these beautiful artist concepts like this one here for TRAPPIST-1e that was put out around 2018 or so, imagining thick atmospheres on these planets, potentially Earth-like, Venus-like, something more representative of what we know and understand from our own solar system. And so since astronomy is, of course, an observational science, we want to know whether this is correct, or whether these are balls of rock, something in between, or entirely unlike what we have in our own solar system. And this is very much an area where we weren't able to make inroads with the Hubble Space Telescope and with various ground-based facilities, so it's very much a cutting-edge question in the era of JWST. And the two techniques that we've largely been using to try and search for atmospheres on rocky exoplanets are transit or transmission spectroscopy, measuring the effective size of the annulus of these planets as a function of wavelength, and then via comparison with atmospheric models, whether they be self-consistent models or inverse Bayesian retrieval methods, trying to map the wavelength dependence of the radius of the planet during a transit with the characteristic absorption features of various different molecular species. Alternatively, by observing when a planet goes behind its star and looking for the excess thermal emission, the photons now coming directly from the planet instead of being absorbed by the host star, and then comparing with how much emission the planet should have if it is a bare rock versus if there is redistribution of heat from the day side over to the night side from a thick atmosphere, which influences how deep the eclipse is. You can then infer at various different wavelengths whether or not an atmosphere is likely to be present. And in my talk, I'll be focusing mostly on results from transmission spectra, but there'll be a couple of results here and there from what we've learned from emission measurements. So as I mentioned, JWST is really the game in town that is enabling us to actually search for these atmospheres. And principally the reason for this, why we need JWST and hopefully soon ground-based facilities like the extremely large telescope, can be understood just on pen and paper in terms of scale height arguments. So if we're comparing a temperate Earth-like planet, let's say in the habitable zone with a hot Jupiter, we have lower temperature, we have a higher mean molecular weight, the gravity can be about similar within a factor of 2 or so, but in short, we have an atmosphere that is about 60 times smaller for the Earth versus a hot Jupiter. And so this naturally attenuates all of the absorption features that we're trying to detect. But there is a way that we can partially recover some ground, and that is via our observational choice of the type of star that we're observing around. So to scale, here is the Earth transiting the Sun, tiny fraction of light blocked, so with current technology it is hopeless to do transmission spectroscopy of an Earth-Sun analog. But if we take the Earth and put it around an M-dwarf star, which is about a factor of 10 times smaller, we gain a factor of 100 in the transit depth, which is largely why the vast majority of rocky exoplanets that we have been trying to search for atmospheres on with JWST have been those orbiting M-dwarf stars. There are, of course, pros and cons of choosing M-dwarf stars. So while there are many advantages, like more frequent transits from, in particular, the habitable zone, if we're targeting those planets being much closer in, we ultimately have to contend with the significantly increased X-ray irradiance or extreme UV irradiance of the host stars, which leads to a very different evolutionary history for these planetary systems compared to our own sun. And so this naturally means that these are going to be very different planets than what we have in our own local solar system. So when it came to the years leading up to JWST, when we were thinking about which rocky planets to target for the first observations with JWST, a helpful observational framework for thinking about which rocky planets a priori may be more likely to hold on to thick atmospheres was this cosmic shoreline hypothesis that, in particular, I'd recommend looking at this paper from Kevin Zarmi and David Catling that really popularized the idea, is showing here an empirical trend from our own solar system that if you plot various objects, planets, asteroids, etc., with the escape velocity versus the insolation from the sun, then the bottom right kind of triangular region is where we observe much thicker atmospheres. And of course, you can go into a lot of calculations looking at the theoretical underpinning of atmospheric escape, but this is purely just an observational diagram that shows that a priori, kind of the further down this way you go, the more likely you are to hold on to a thick atmosphere. And you can make plots similar to this for known rocky exoplanets, but of course this is just for the sun. We don't know whether the gradient of such a trend will differ, or if there's a difference in the offset, but it at least gives you an idea of where you're more likely to find thick atmospheres. And so a lot of the planets that were chosen for initial cycle 1 observations with JWST were chosen to straddle this cosmic shoreline, depending as well on the observational feasibility. So there are a lot of rocky exoplanets now that we're 3 and a bit cycles in with JWST that have been observed, and I won't be able to talk about all of them. So I've chosen a kind of representative sample of some that either that I've worked on that I know well and are dear to my heart, or I think are just, you know, fantastic illustrations of what we have been able to accomplish with JWST. And so this is kind of the roadmap for the talk. So I'm first going to focus on 3 planets in particular that were observed as part of the Cycle 1 No Air program, GEO 1981, led by Kevin Stevenson and Jake Lustig-Jaeger, that had the goal of targeting 5 rocky exoplanets that are in the vicinity of the cosmic shoreline. So this plot here is actually kind of flipped around from the one that we were looking at previously by having the equilibrium temperature on the x-axis. So the bottom right triangular region is where a priori we do not expect to see thick atmospheres retained over time. So the first 3 planets I'm going to talk about, in particular the first one, LHS 475b, is thoroughly where we expect there not to be a thick atmosphere. So, and then later on in the talk, we'll look at some that are in the region where we would expect an atmosphere to be present. So let's start with LHS 475b, which is the first rocky exoplanet that was observed by JWST in 2022. And funnily enough, for kind of the historical viewpoint, LHS 475b was actually a planet candidate at the time that these JWST observations were executed with the NIRSPEC G395 instrument. So this is also the first Earth-sized exoplanet that was confirmed by JWST. So what does the transmission spectrum look like? Well, it's very flat, but you can still learn things from a flat spectrum. So what is shown in the upper panel here in this figure made by Sarah Moran is that if LHS 475b were to have a hydrogen-rich atmosphere, we would expect to see very large absorption features, in particular from methane here at 3.3 microns and carbon dioxide at 4.3 microns, which are not observed. But the precision is such that you can even start to differentiate between classes of rocky exoplanet atmospheres or high mean molecular weight atmospheres. So with this zoom in the bottom, you can see that atmospheres that are clear and composed of 100% methane, the kind of dark greenish line here, are inconsistent with the flatness of the spectrum, and similarly, atmospheres that are still hydrogen rich but are 1,000 times solar metallicity should have a strong carbon dioxide feature that are not observed. So by running a retrieval analysis, and what this plot here is showing is that the coloured kind of smudgy hazy colour is where is still consistent with the flatness of the spectrum, while the dark black regions are ruled out. You can start to see that clear variants of Titan or of the modern Earth are not consistent with the transmission spectra flatness for LHS 475b, but more cloudy or hazy variants of Titan or like Venus are still consistent. So you can still concoct atmospheric scenarios that would not have these atmospheric absorption features, but what this demonstrated was the first proof of principle that with JWST we can start ruling out classes of rocky exoplanet atmosphere. Okay, now let's go on to the super-Earth, GJ486b, which is one of my favorite planets in this talk. So we observed through the NOAA program 2 transits of GJ486b with the same instrument as shown on the previous planet, NIRSPEC G395H. This planet is also one where a priori you'd expect it to be difficult from cosmic shoreline arguments to hold on to a thick atmosphere. But when you combine the 2 transits and produce a transmission spectrum with 3 independent data reduction pipelines, what we found very curious here is that unlike LHS 475b, if you just kind of fit an agnostic Gaussian model where you just fit for a Gaussian that can have variable width and kind of slide back and forth, statistically at around about the 3 sigma level, this appears to prefer there to be a slope towards the short wavelengths as opposed to it being a flat spectrum. And so then we got excited, we started running atmospheric retrievals to see what could potentially explain this deviation from flatness. And very quickly, we found that if there were to be an atmosphere of pure water, a hot steam world, then you could explain this rise towards 3 microns via half of a water absorption feature. So this is pretty much me at that point. Yep, good likeness. I was getting really excited about a water-rich atmosphere, but then we took a step back and tried to look for other alternative explanations that could explain the rise, and very soon established that it's not a unique solution. If you have unocculted star spots outside of the transit chord with no atmosphere on the planet, that can also produce a statistically identical, a degenerate model. But what you see here is that although over the wavelength range of G395H, these models are perfectly degenerate, they deviate at shorter wavelengths, which we'll come back to a little bit later. And the reason why these models look so similar is because we're still seeing water absorption, but the question is it coming from cool star spots on the host star, or is it coming from a planetary atmosphere? And what is going on here is a phenomenon called the transit light source effect. Essentially, if we have a planet transiting across a quiet region of the host star's surface, while the overall integrated spectrum of the star itself contains multiple active regions, that leads to a difference in the out-of-transit spectrum of the star from that is illuminating the planet and any atmosphere that it has. And when you propagate this forward into the transmission spectrum, you can essentially get ghost absorption features imprinted into the spectrum, even if the planet itself is just a ball of rock with no atmosphere. And in the most complicated situation, you could have a planetary atmosphere and you could have these active regions. So we have to be very careful when conducting our models and atmospheric retrievals to test both scenarios and try and disentangle what this effect is actually doing. So that is illustrated here, where these two different fits could be explained with either a 100% water atmosphere, shown in the blue histograms on the bottom right, or with roughly 10% of the host star covered by cool spots that are about 500 Kelvin colder than the photosphere. But what we are working on right now, actually, is we just obtained over the summer 3 transits with the nearest SOS instrument to try and directly test that we would expect to have a large upward slope at short wavelengths from unocculted star spots, while we should continue to see multiple water bands if it is a water-rich atmosphere. And we only very recently obtained these observations, and we're working on all of the atmospheric modeling now. So I won't spoil the results right now because, yeah, they are evolving over time. NIRISS is a fun instrument to deal with. But what we do know is from complementary emission observations in this paper from Megan Mansfield, is that from the mid-infrared MIRI-LRS observations, you see in the bottom panel that there are various classes of thick atmosphere that appear to be inconsistent with the MIRI emission spectrum. In particular, 1 bar atmospheres composed of water appear to be inconsistent with those observations. So if there is to be a steam world atmosphere on this planet, it would have to be a thin steam world. Like in the top panel, a 10 millibar pure water model would still be consistent with the lack of prominent absorption or emission features seen in this spectrum. So stay tuned though for a even more precise transmission spectrum over a wider wavelength range that will be coming out for this planet in the months to come. Okay, so onto our third planet, GJ 1132b. And this is a fun one for those of us that are old enough to remember the Hubble Space Telescope observations of this planet. Because back in 2021, there was a Hubble WISC 3 spectrum that was published by Swain et al., potentially showing a hydrogen cyanide absorption feature at 1.55 microns and a slope that could be attributed to highly scattering atmospheric haze. Independent reanalyses, though, found instead that you can get a flat spectrum depending on the details of how you do the data reduction. So this has been a very contentious planet. There have been multiple papers written over the years with the title Detection of an Atmosphere on the Super-Earth GJ 1132b. And so this was naturally a planet that we wanted to observe with JWST as soon as possible to try and establish whether or not there are strong atmospheric features from this planet. So we similarly observed 2 transits with, again, the NIRSpec G395 instrument in 2023. And what we found is from the first visit, we got pretty excited because, you know, it looks like even by eye, there might be a slope towards the short wavelengths, maybe an absorption feature at 4.5 microns. But then we made the mistake of observing a second transit that was completely flat. So this was actually kind of led to a tricky, almost philosophical issue when it came to the atmospheric modeling, because these spectra were inconsistent at the 3 sigma level if they were just random draws from the same distribution. So we didn't combine them together into a stacked transmission spectrum, and instead treated each independently, like we had only obtained that spectrum, to see how different the answer could be. And what we found is that the first transit, if that was all you had obtained, you would be quite convinced, at least the 2 borderline 3 sigma level, that you had detected a steam world with about 1% trace methane in the atmosphere, which is shown on the left. While on the right, it's a completely flat spectrum. You do not need an atmosphere. You don't need stellar contamination or anything. It is just flat. So you could try and concoct ways to reconcile this, like, oh, well, maybe the second epoch was cloudier, but you would need to have a completely clear atmosphere in the first visit, and then an optically thick cloud at something like 10 or 100 microbar. Like, it just doesn't seem to be plausible to have that level of atmospheric variability. So at this point in time, we thought it was most likely to be an astrophysical or instrumental systematic affecting these two transits. We couldn't reconcile it with differences in the stellar contamination because by fitting the stellar spectrum outside of the transit, you get the exact same overall kind of star spot coverage properties. So, but what this underscores though is that if you think you have detected an atmosphere on a rocky exoplanet with JWST, multi-transit repeatability, ideally with the same instrument, but even better, if you have multiple instruments seeing the same thing, is the best way to be confident because these are small signals and we don't know how to model the host stars accurately. So observe these planets multiple times before claiming that you've confidently found an atmosphere. Similarly, in this paper from Chao Shui et al. With MIRI LRS emission, you can see maybe there's a hint of an absorption feature around 6 microns or so, but there's very large error bars because it's very tricky once you start pushing down to these cooler rocky planets to obtain emission spectra. But then you can start kind of playing a game with chi-squareds and looking at which types of atmospheres are ruled out, and in particular, pure carbon dioxide thick atmospheres are inconsistent with these observations. But things like a 10 millibar water-rich atmosphere would be statistically consistent with the emission spectra. So prompted by this, we observed quite recently 2 additional transits of GJ1132b, and that was published just a few weeks ago. You'll see this in this paper led by Katie Bennett. So we now have a 4-transit transmission spectrum of this super-Earth. The 2 follow-on transits we observed with the G395M instrument to remove any issue of kind of this detector gap or relative offsets that have been seen by some programs. And what we found overall, the TLDR, is that the spectrum is flat. It looks like the first transit was an outlier all along, and the 2 additional transits were more representative of the second visit. So the atmospheric inferences we derive are really skewed depending on whether you fit the 3 flat transits or all 4 of them together, because that puts in more of a slope towards the short wavelengths. So we kind of summarize these constraints on the plot on the right. The stars show the constraints from the emission spectra results from Chao Shui. But what you can see is that hydrogen-rich atmospheres for any surface pressure completely ruled out. You could still statistically have a very thin water-rich atmosphere, like 10 to the minus 4 bar, but the favored results from the transmission spectrum would be a thick carbon dioxide atmosphere, because then the high mean molecular weight squashes your absorption features and makes it flat. But we know from the emission observations that there can't be a thick carbon dioxide atmosphere. So when you kind of combine these 2 different constraints together, the most likely answer is that GJ1132b is just going to be a bare rock. So complementary observations from transits and eclipses are really the way to go to try and resolve these degenerate solutions. So let's now move on and look at the favorite planetary system of many rocky exoplaneteers, at least before JWST started telling us what these planets are most likely to be. So let's take a look at what we've seen so far from the TRAPPIST-1 system. So, and I think this is particularly telling because I'm sure many of you will remember the big press release that came out around 2017 with the discovery of all these planets, with these beautiful artist concepts imagining TRAPPIST-1 D, E, and F in the habitable zone with liquid water on their surface. So many hundreds of hours of JWST time over multiple cycles have been devoted to searching for atmospheres on the planets in this system. And a lot of the theoretical work that myself and many others were involved in looked at how many transits you would need to detect carbon dioxide, methane, water, and potentially even prospective biosignatures like nitrous oxide and ozone, finding that in the absence of stellar contamination, which was not routinely included with this early theoretical modeling, between 10 and 100 transits should let you confidently detect atmospheric molecules. So the first transit spectra of any of the planets in the system in this paper led by Olivia Lim showed immediately that stellar contamination is a significant issue. The wavelength variation is on the order of 10 times stronger from stellar contamination than the atmospheric features that we're searching for. And it also significantly varies from transit to transit. So while the first transit shows kind of a rise towards short wavelengths that is characteristic of unocculted star spots, the second shows a decrease, which is instead characteristic of unocculted hot active or vacuolar regions on the host star. But you could completely explain these observations only with the stellar contamination without needing to invoke any atmospheric absorption from TRAPPIST-1b. Similarly, the eclipse detected in the mid-infrared at 15 microns in his paper from Tom Green showed that the total amount of thermal flux being emitted at 15 microns from TRAPPIST-1b is consistent with what we would expect from a black body at the overall equilibrium temperature or dayside temperature of the planet. While if we had a thick carbon dioxide rich atmosphere, instead you would expect to struggle to detect the eclipse, because then you would have absorption from CO2 that would pull you down to around where these green and red lines are here. So by measuring a very hot dayside, that indicates that very likely TRAPPIST-1b is just a bare rock without any significant heat redistribution from an atmosphere from the day side to the night side. So probably a bare rock for TRAPPIST-1b. It's kind of a similar picture for TRAPPIST-1c. So the eclipse, in this paper led by Sebastian Sieber, showed that, again, there is a quite deep eclipse centered on this carbon dioxide feature. So I'll kind of highlight the dashed lines here that, depending on the exact details of how much heat is redistributed for different black bodies, you can move this up and down a little bit to be consistent with the error bars from this point here. Technically, you could still have a little bit of carbon dioxide absorption from a thinner atmosphere, which is shown by this kind of green model here. So it's not, completely conclusive that there is no atmosphere from the eclipse, but at least you can see that there is no thick atmosphere dominated by carbon dioxide. The transmission spectrum of TRAPPIST-1c from Michael Radiker again shows significant stellar contamination from the host star, but if you model the stellar contamination in a retrieval framework, divide out the best fitting model, stack the two transits together to produce the spectrum shown on the right here, and there's a lot of caveats there about how correct the stellar models are, like very active area of research there. But essentially, you're left with a residual flat spectrum, and if you then fit it for different assumed pure atmospheres, like pure water, ammonia, carbon monoxide, and methane, you find you need to have a very low effective surface pressure to render the spectrum flat. So from the transmission spectrum, there are not thick atmospheres dominated by water, ammonia, CO, or methane. And from the emission, we know there is not a thick carbon dioxide rich atmosphere. So, you can always still find atmospheric models that are consistent, like a very cloudy or hazy or a very Mars-like thin atmosphere. But the very thick atmospheres that we were hoping would immediately pop out the data are very much not. And the breaking news, really, for the TRAPPIST-1 system in this paper from Caroline Pialet of TRAPPIST-1d that just came out within the last month or so, provide very stringent constraints on potential atmospheres. So again, we have two different transmission visits with different stellar contamination in the two epochs. But if you simultaneously fit for the stellar contamination and for a common atmosphere, or if you do a similar thing as for TRAPPIST-1c, where you divide out the best stellar contamination spectrum, you can obtain the partial pressure constraints shown on the right. So the colored regions that for a nitrogen-rich atmosphere with methane is kind of all pushed up into the top here, and for a nitrogen background gas with carbon dioxide as an absorber, in these blue contours here, you can see that the black exclusion regions are actually ruling out a significant phase space of atmospheres like what we have in our own solar system. So TRAPPIST-1d despite being a planet that nominally is just within the habitable zone, does not have an atmosphere like Earth, either the modern Earth or the more ancient Archean Earth. It's not like Titan, it's not like the early Mars, it's not like a kind of clear variant of Venus, potentially a very cloudy or hazy thin Venus-like atmosphere, or a very tenuous Mars-like atmosphere, could still be consistent with the flatness of the spectrum. But really this has ruled out thick atmospheres being retained. And when all you're left with statistically are thin atmospheres that very likely could just be stripped away by the host star, the most likely answer a priori is probably just bare rocks. So yeah, this is where we are for TRAPPIST-1 at the moment. And I will say, watch out, very, very soon, TRAPPIST-1e is coming out very soon. Okay, so since the original title of the talk was Promising Signs, let's look at some planets that are maybe a little bit more promising than the probable bare rocks we've seen so far. So let's go on to L9859d. So what is really exciting here is that in these NIRSpec G395 observations, there are spectral features that are observed that you can't really explain with unocculted star spots, or it's just not really a good model. So the spectral modulations shown here appear to be best fit by either hydrogen sulfide, H2S, or via sulfur dioxide, SO2. And unlike the case where if you see a water absorption feature, it could be from unocculted star spots, you wouldn't normally expect to see H2S or SO2 in a star spot. So if you detect these molecules, they're almost certainly coming from an atmosphere on the planet. But I should say that the author of this paper in particular, and I know Agnes in the audience here, and Amelie Gressier led these two papers. This is not yet at the detection stage. There's not yet a kind of a conclusive lower limit on the abundance of these gases, but there are more observations coming of actually all three planets in this system. And what is exciting here is that not only are there potential hints of atmospheres, and SO2 features are being seen for both 9859d and for planet B in the system, but there's also a theoretical mechanism for why we would expect to see gases like SO2 on these planets, which makes it more plausible. So essentially, it's a similar mechanism than was proposed a long time ago for the volcanism on Io. So kind of, tidal heating of the interior of the rocky planets in the system that can warm up the interior and lead to outgassing of these volcanic gases. And for all the details of this theoretical framework, check out this paper from Dan Seligman. So this is definitely one of the most promising rocky planet systems that we have so far around an M-dwarf. And the last planet that I will highlight is LHS 1140b, which is a planet that is firmly within the habitable zone. And in the framework of the cosmic shoreline, LHS 1140b is even more likely a priori to hold on to an atmosphere than the Earth. And the last time I checked out the window, it looks like we do indeed have a thick atmosphere. So we're feeling pretty optimistic a priori for LHS 1140b. It is a little bit colder than the Earth, and so you would need to have, a thick atmosphere in order to render it habitable. So in papers by Charles Cadot and also by Mario Damiano, transmission spectra have been observed of LHS 1140b. And what I'm going to be focusing here on the nearest SOS short wavelength observations, for which we do see stellar contamination. There's a weak hint of this kind of downward slope here, but it's not as prominent as has been seen for TRAPPIST-1. This is a less active M-dwarf star. And you can see here the significant improvement from the Hubble observations shown by the white diamonds and the JWST observations. But what was particularly puzzling and exciting is that when we simultaneously fit for the presence of a planetary atmosphere and for the stellar contamination, the atmospheric retrievals kept kind of rushing up to 100% nitrogen. And that was a puzzling thing. We kept trying to kill it, trying different atmospheric scenarios. But ultimately, what helped us the most for figuring out why this is going on is that if you divide out the stellar contamination model, the data appears to have a residual slope towards the short wavelengths. And so by including an atmosphere containing molecular nitrogen, Rayleigh scattering from molecular nitrogen kind of added in just enough of a slope that you could better explain this by having kind of a flat atmosphereless planet. Now, we're not claiming an atmosphere. This is very low significance. Um, Best is said about the 2 sigma level. However, we won't have to wait long in order to establish if there is an atmosphere on this planet, because there are observations that have already happened and are scheduled over the coming year and a bit through the Cycle 4 Cosmic Shoreline program, led by Jake Jaeger and co-PI'd by Kevin Stevenson, where we're getting many more transits coming down of LHS 1140b. So, but I just find this to be a very conceptually beautiful planet, because if there were to be an atmosphere like this nitrogen-rich atmosphere with at least 100 parts per million carbon dioxide, you could potentially have an ocean on the day side of the planet larger than the Atlantic, producing this kind of eyeball-like ice world. And the last thing that I will just point out is that the Rocky World's DDT program has now started and is really going to help with providing both complementary emission observations and also observations to help prioritize which planets to do deep lux via transmission spectroscopy. So the 4 targets that have already been chosen via this emission photometry program combined with Hubble UV spectra are shown in this table in the bottom right. And I note that very recently, just on arXiv, kind of the first observations were posted in this paper by Chao Shui, showing that GJ3929b probably is a bare rock. No carbon dioxide feature was observed here. So yeah, so with that, I will leave up my conclusions, and I'll emphasize that, these have been perhaps not as exciting as we were initially hoping. We're seeing some probable bare rocks across the board, but don't lose hope, because the easiest planets to observe were always the hotter ones that were less likely to have atmospheres. And it's really now the time, as JWST is maturing, for us to find the best targets and really go deep in order to search for these small features that were always going to be hard to detect. And yeah, with that, I will also say St Andrews is a beautiful, beautiful place, and keep an eye out in the near future for job postings, in particular for master's projects and for PhD positions, and probably in a year or two postdocs, because I'd love to have you up and join our Exoplanet Atmospheres group up here in Scotland.
Well, thank you. That was a wonderful talk, and no need to apologize for a bunch of bare rocks at times. It was still fascinating.
Nature is what it is.
Yes, yeah. I think it would be unfair to hold you accountable for what nature does. So with that, if we have any questions, raise your hand and you can unmute yourself. Okay, James, go ahead.
Thanks, Duncan, and thanks, Ryan. That was a great talk. And I suppose, yeah, welcome officially back to the UK and to the Bowie Plus network. It's great to have you back. Uh, Regarding LHS 1140b and the N2 rich atmosphere, have you sort of considered the likelihood of generating such a N2 rich atmosphere with a lack of, other species? Um, yeah, that was my question.
Yeah, yeah. So I should say that although the N2 was the only thing that was popping out of the atmospheric retrieval analysis, you could still have abundances of other species. So in particular, you see carbon dioxide here. Statistically, you could still have a 100% CO2 atmosphere that would flatten the spectrum or trace amounts of CO2. So it's not saying, because it would be weird to just only have N2. You could also have, mixtures of, you know, abiotic O2 that would produce a similar kind of like scattering slope. This is purely a statistical phenomenon. So we did not do here kind of detailed modeling in terms of outgassing to assess the plausibility. But there has been general circulation modeling done for LHS 1140b that does show kind of the plausible atmospheric scenarios that you can have, which does include a significant amount of nitrogen. But you would need to have some additional CO2 in order to get that kind of ocean that I was showing there. So you can't just do it with pure nitrogen. So, oh, and sorry, James, for not including your particular planet, that we all appreciate the work you did in the talk. Too many planets.
No problem. No problem.
Agni.
Hi, Ryan. Great talk. Thanks for including the planet. I was just wondering, what's your take on stacking transits? Because we've seen like these differences in different transits, and the original plans for most of these observations were to stack tens to multiple transits at least. So if we are actually seeing variability from, say, stellar contributions or maybe even physical variability in the planet, is it possible to quantify how much that would affect the stacking process, or if it's even possible?
Yeah, it's a big worry. So, I mean, our approach has just been that if the transits are statistically consistent with kind of random noise fluctuations, then you're probably fine just stacking them together. But if by eye you see these significant differences like we're seeing almost across the board for TRAPPIST-1, then you just can't stack them. Then you have to do something like simultaneously fit for each of the transits individually together with, say, a common atmosphere, which will be consistent in time, but then time variable stellar contamination. And that's going to be hard because for TRAPPIST-1e, for example, and obviously you'll see more about it when our results come out, we have 4 transits there. And I won't spoil the results, but there are big differences between the visits. And in total, there's going to be 19 transits of TRAPPIST-1e. And I dread to think about trying to do a retrieval with 3 or 5 stellar contamination parameters per visit plus a common atmosphere. So we're going to need more inventive approaches there when we have this significant variability. There are other approaches people are taking, like trying to do double transits or consecutive transits to try and empirically normalize out the stellar contamination and then stack the relative transmission spectra, which could be an approach. But it's very much an active question that you kind of have to take on a system by system basis by looking at your spectra to see whether you can stack or not.
Thanks. That's great.
William.
Yeah, thanks. My question was about, do you know what the limit for JWST is in terms of how big a star we can begin to look at? Like if we're facing problems with the stellar activity of M-dwarfs, is it possible to move off of them into slightly larger stars, or is this sort of as good as we can get for the time being?
For rocky planet, yeah, I mean, if you have enough time and patience, then sure, you can push up a little bit into like a K stars and things. I don't know off the top of my head kind of the exact like kind of threshold like limit, but we've not seen any obvious signs of just a noise floor when it comes to stacking. So if it does turn out that the vast majority of M-dwarfs are just if all the worlds are just barren wastelands that have had all their atmospheres stripped away, then it just means we have to be more patient and kind of gradually commit to some of those larger stars that are likely to be less active. And in particular with, I was talking about LHS 1140b, because it's sufficiently cold around an inactive star. Realistically, if you really want to be confident of an atmosphere, you need to stack about nine transits together. But you can only observe 3 or 4 transits a year. So you have to be very patient with some of these systems due to limited observability windows. So it probably just means that, I mean, if you think about it, Hubble, we're up into cycle like what, 34, 35 or so at the moment. There's still new science coming out of Hubble. Right. So long as JWST still remains to function, it could very well be that it's taking until cycle 10 before we're really getting some like solid statistical evidence of rocky exoplanet atmospheres. And of course, this is all in the M-dwarf regime. I know we've obviously got all of the debate about kind of 55 Cancri, for example, which is not around an M-dwarf, which is why I didn't speak about it today. So there are ways that you can still look at rocky exoplanets that aren't just around M-dwarfs.
Okay. Thank you.
Do we have any other questions? In that case, let's thank Ryan again for a lovely talk. Next month, we will have Angeli Piet giving a talk about sub-Neptunes, so going to a bit larger.